do a sound check very quickly. Very good. That's all we wanted. And yeah, that, I don't know, it's the best mic I have, you know. Okay, so let's pull up two things. And those things are the course website we're using, and then we're going to find theory of, well, I just have the link here, right? Oh, I don't have the link there. That's my bad. I'll try and add that. Open course. Okay. So what's going on here? This is Professor Sipser, who wrote our book. Okay. There are lecture notes, and this is much easier to see if it's full screen, so I'm going to make it large again. There's lecture notes. Okay. This stuff should look familiar to you. Finite automata and regular expressions. Non-determinism closure property regular expressions. Regular pumping lemma, finite automata, regular expressions, CFGs. You see, that is exactly our first day, those 3 lectures. And I want you to feel like you're getting your money's worth. Each of these is a 1.5 hour lecture, and every other one of them has a 1 hour recitation. So this is 4 hours, and this is 2 hours, right? So that's 6 hours on the first day, plus the 1 hour for aims of education, right? Okay, basically did the same thing the next day, though we actually got a little bit further. We did push-down automata, CFGs, the CF pumping lemma, and then we took lunch, and then we did Turing machines. We did Turing machine variants, and those variants were multi-tape,
single tape,
and non-determinism. Yep. I just talked to you for an hour about the Church-Turing thesis because it was the end of the day, right? And then we started with decision problems. We're halfway through this right now. So that's, what is that? 1, 2, 3, 4, 5, 6, 7 45-minute lectures. There's 7 things of an hour each. So you got 7 hours that day as well, right? This lecture here was the one I was planning to get through, and then I looked at it, and it's a lot of material. So the original plan was we would finish this today. Actually, we're going to cut halfway through that. And then the final one, I'll introduce undecidability in a lecture. Now, after that, I have to make a decision, because my inclination is that this stuff is not part of computability theory. Perhaps reducibility is, but these ones aren't. And that I should start time complexity. So the things that I have scheduled for us to do while we're not together are time complexity, P and NP, NP completeness, and the Cook-Levin theorem. When I took complexity theory, my final exam was prove the Cook-Levin theorem. You walked in, they handed you a booklet, you wrote the proof, and you either passed or you didn't, and I got a C+. So I technically passed. And it was like the 4th highest grade in the class, so you know. And then I have to tell you a little bit about space complexity. Now, a lot of this stuff, no one does this, okay? Oracles are interesting. This stuff is kind of interesting. We use BPP in complexity theory a little bit. IP, very complicated. Co-MP, very complicated. So this stuff is perhaps even beyond my ability to teach, or even understand, much less teach, right? And when Professor Sipser is talking about the class in these ones, he's like, it's gonna get a lot harder. And so I'm really worried about this one, which is you're gonna write a proof that proves there's a machine that can prove itself. It's like, so that's sort of the plan. Now, there's PDFs and PPTs. I used the PDFs because the PowerPoints, I never really assume a PowerPoint's going to work the same way on my computer it works on someone else's. That's no problem. I'm not going to play one of these lectures because YouTube will content strike me, right? We are in one of these ones. I don't know. So you have quite a bit of time of lecture content. These things are, the lecture videos tend to be 60 to 75 minutes because they take a coffee break in the middle. So it won't take you too long to watch them. I watched them on 2x speed. I don't know if that's going to work for you. But when I was making my course materials, I had Professor Sipser on this monitor, and then I was figuring it out in Quarto Markdown on my monitor, and that was all, right? There are recommended readings, so you are recommended to have read sections 1.1, blah, 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 blah. We're right here, right? I wasn't assigning readings because I've never read a textbook in my life, including when it was assigned. If you do well with textbooks, you should read them. Here's the link. And you can probably buy one for not that much if you want a physical copy. I don't know where you'd get one, right? I would probably just go to here. I'm assuming they print it, right? Sipser Theory of Computation. One of the advantages of taking this course specifically as Sipser put things together. Oh my gosh, it's $95. Never mind. Didn't do it. Oh well, no, 42 maybe. Oh, paperback 13. Actually, I would buy one of these for $13. Okay. There's a really strong advantage, particularly in this course, in taking the version that's taught at MIT, and that's because Chomsky was at MIT. And Chomsky did a lot of this stuff, right? In addition to other things, Chomsky was probably better at explaining it than other people, which is probably more important than being able to understand it. So I'm assuming Professor Sipser has actually met Chomsky, and the reason some of this stuff makes sense to him is because he met Chomsky. I've never met Chomsky, but I watched Professor Sipser's lectures, and I was like, oh, this is much, much better than what I got in undergrad, and I went to like UChicago, one of the best universities in the world or something, right? Didn't really matter. And so like the professor that taught my class was an excellent complexity theory researcher, possibly the best in the world, right? And it didn't help me a lot, right? Professor Sipser did a very good job explaining it. So if there's something I don't understand that you want to hear from someone else, that's the first person I'd go to. And if neither of us explain it in a way that makes sense, that probably means you need to review some mathematics or something, right? And then how you do that is on your own, but you can ask me questions and I can provide resources. Okay, with all that out of the way, let's talk about what we've done so far, which is quite impressive, and there's a lot of it. Professor Williams said, I'm making you drink out of a fire hose, but that's what you signed up for. So here we are. Okay, or no, we should always talk about the aims of education. So in a minute, I think we should write a thank you note to Onyinye and tell her to thank the other people for us because we're going to drop her Kiev when we leave. There are aims of education other than getting really good at thinking very fast, right? And one of them, I think, is like having an appreciation for things other people have done. One of the things I really liked about Amber Huffman's address is this just notion that none of us is as smart as all of us. That's a sort of refreshing thing to have, and it's one of the things I really like about computer science versus some other disciplines. Academics, all academics, me, have a tendency to get sort of stuck in their rut and not want to work with other people because it's a lot of work to work with other people, right? There's always some nervousness with a CS program that, oh, you're not training students to do enough group work. I think that's not so much a risk. I don't think it's very often the case that software developers are like, I mean, they do look at each other's screen, but like when everyone went remote, the software engineering seems to have probably gotten better, right? And I think the distraction-free work environment was just as big as having collaboration, right? That's not so important as having the approach to caring about working with other people. Believing that someone already solved the problem you're trying to solve, looking into what other solutions are, making sure you're doing something that follows best practices, being engaged with your professional community. So I'm a member of the IEEE, the something Electrical Engineers International. I don't know. The I and two of these are electrical engineering. I don't know what the 30 is. And the Association of Computing Machinery. And you don't need to join those organizations, but it's important to be aware of like what their standards of ethics are and things like this. And the reasons to do that is it's good for you and it's good for everyone else, right? I thought Amber Huffman did a good job talking about that. I am much less convinced that AI is the next big thing than everyone else. I understand there's a lot of money in it. One of the things I hope you take away from this course is in 1936, 37, the Church-Turing thesis came out, and they said, we think anything a human can compute, a computer can compute. And now there's these big AI researchers going on. They're like, we have computers as powerful as humans. And it's like, no, we have those in 1937, right? So whatever you think the big results of AI are, right, it seems like they were actually developed by these theoretical mathematicians 90 years ago, right? And I'm very proud of everyone, and I'm glad they're happy with their large language models, right? But I haven't seen one of them do something that surprises me. And it's okay they're surprising and impressing other people, but I don't think they're surprising and impressing anyone that's seen this material. Because the difference between not being able to write a program that accepts a string and being able to write an LLM that essentially accepts a string and then returns another string, it's not that big of a leap, right? And especially the strings are usually not that impressive. This is unrelated, but because everyone asks about AI all the time, one of my slides today, I was quite sure I was teaching something that an AI could write the slides for, and it could not. Because I thought it was a very simple technical concept. I said, hey, I have this example. Can you just expand this example and do step by step? And it couldn't do it because I didn't want to type the markdown myself. That's all. So even like a fairly basic thing in theoretical computer science, it cannot do. You are sort of both lucky and not lucky that the AIs seem quite good at Python, which means there'll be more pressure on you to be better than the AI, but also it'll be easier for you to become better than the AI. So this will affect you before other people. It seems slightly worse at JavaScript. Okay. What is a finite automata?
Sigma.
Yep.
Delta.
Yep.
Then finite state.
Yep.
Initial state and accepting state.
Very good. That's what we have right here. Under the finite automata. No, we should go back. What do finite automata do? What do they compute? What do they calculate? I have a finite automata. It's a machine. And that machine has some inputs and some outputs. What are the inputs and outputs of a finite automata? This is the useful. Sorry?
Strings?
Yes. There's strings from the non-empty set of input symbols. So you have some number of these, some finite number of these input symbols on a tape. We now say. We used to just say as input. So the input is a string, and what is the output? True or false? Accept or reject?
Accept or reject.
Yes. So for all strings, the subset of strings for which the automata says true is the language of the automata. And that's how we create languages from automata. That's the correspondence. I think there's just fundamentally no way around this being kind of confusing. That automata and languages are not the same thing, but they represent the same thing through this notion of recognition or acceptance, right? The language of the automata is nowhere in this tuple, right? It's an emergent property. It's when we turn this thing on, it has some capability. It is the same way that the Python interpreter is different from all possible Python programs, right? It's that sort of difference, right? Perhaps an automata is a compiler, right? And so, why do we ask this? Well, we very rarely prove properties about features of the 5-tuple itself. What we do is we manipulate and fiddle with the 5-tuple in order to show that we have some property. And so here's an example of one property we want to say. I have two machines. They are deterministic finite automata in this example, but this also works on, now we have shown, non-deterministic and generalized finite automata. One of them accepts some strings and one of them accepts some other strings. One way to think of this is M1 accepts the passwords from students, and M2 accepts the passwords from faculty, and the union of those two things are the people that are allowed to use the campus Wi-Fi. It's as simple as that, right? Or perhaps we say they accept the combination of a student ID and a password, something of this nature, right? So this is an example of union. Commonly think of this as branching or something. And what do we have here? Well, we have the set of finite states. So that is a set of finite size, essentially. What are the states? They're nothing. They're symbols. They're ideas. They don't physically exist, though they could physically exist if we built one of these out of mechanical means, like Turing proposed. We have the set of letters. Those are the things we can write on the tape, right? These are of great interest to people that do like AI vision image recognition, which is now basically a closed field because the AIs are so mature. We have some delta. Delta is one of these things. We have the accept state, or we have the initial state and the accept state, right? So if we want to accept both things, we simply, quote, run both machines in parallel. What does that mean? Well, no trouble at all. Our machine is non-deterministic, which means if it sees an if-else, it can follow the if and the else. It does not care. It executes both of them simultaneously, and it can do this because it's magical, because it's not real. The important thing is just the idea of whether it works. And in practice, the way it works is it just checks one path and then the other, and that's completely reasonable as well. So what do we do? For our union, we take the cross product of Q1 and Q2. What does that mean? Well, we take every set in both, right? That should be union. That's disjoint union. This is part of the NFA proof. That's what's going on here. That should be disjoint union. We take the same alphabet. This delta, I understand it has a lot of parentheses. I know students, when I put this stuff on the board, they always say, ooh, I'm not sure I quite understand that, so I'm going to explain it to you, and that's not going to help you understand it, but it's going to make me feel better, right? Okay. The things in this theorem are that we have, yes, no, this is cross product. Okay, this is just a non-deterministic case. Okay, so we have a pair of states. Q corresponds to a state in Q1, which comes from machine 1, which comes from the first language. Q prime refers to a state in Q2, which comes from machine 2, which corresponds to the second language. Perhaps this state measures whether or not you have a faculty username, and this state measures whether or not you have a student username, right? Perhaps, right? It reads some character A. Okay, why is this a pair? Well, this pair, remember, we said the states aren't actually anything in particular. So differently in this union, M3, we say, our states are not whatever the states were in Q1 and Q2, but they're actually ordered pairs of states. Or I think it can be a set of states. It doesn't matter. It's just you have to track two states at the same time. You have to remember two thoughts at one time. And this is the thing that doesn't really correspond that well to lines of code, but you are executing two lines of code at the same time. Just a little bit goofy, right? But not impossible. We've seen multiprocessing. Okay. So these are the two lines of code I'm executing when I read some character A. And why is that? That's lowercase a to correspond to a member of the alphabet, if that makes sense to you or not, right? Okay, and so the way we're going to figure out what the next states we're in are is, well, we're going to be in a pair of states next time too. But we already have two functions, delta 1 and delta 2, that take a state in Q1 and a letter in sigma, and they return a state in Q1. So we take the state in Q1, which is this state, the first state, and a letter, which means this thing, the return value of that, when we evaluate it, it will be a state within Q1 in the set of finite states. So this is one of the finite states, Q, and then this is also one of the finite states. We don't know what finite state it is because we don't know what Q and A are, right? But it's one of them. We do the same thing for Q2. So what that means is that this part right here, if I highlight all of that, nope, I have to go one more. Oh, Oh no.
And the break.
No, we don't get shake breaks. Okay. You can have a break when you've earned it. Okay. This bit right here, this is it's enclosed in parens, as you see. This is an ordered pair. And so, what this means, oh, this comma is supposed to be there. The comma's just in the wrong place. Okay. This is an ordered pair of two states, and one of the states, because its return value of delta 1 is in Q1, and one of the states, because its return value of delta 2 is in Q2. So I take a pair of states and a letter, and I get a new pair of states. And those pairs correspond to where I am in each of the two things. So perhaps we say, M2 says you entered a username, and it's not a faculty username, and M1 says, you entered a username, and it is a student username. So one of them is in the username correct state, and one of them is in the unknown user state. Makes no difference, you will progress. Okay, these are the initial states. We begin in both state, perhaps in our motivating example, who are you and who are you, right? They don't know who you are until you start typing in your username and provide the string. The acceptance state is not too bad. We take all of the states that accept in M1 and all of the states that accept in M2, and you just have to be in one of those two states across your pair. So this accepts whether either of the first or second element of the pair of states is an accepting state. Why do we do that? Well, to log into campus Wi-Fi, you do not need to both have a student and a faculty login. You only need one. And so if you have a student login, you will satisfy F1, and if you have a faculty login, you will satisfy F2, and we are both able to access the campus Wi-Fi. Good for us. I'm pretty sure I actually just have a student account, but that's okay. It doesn't matter. I'm trying to figure out what my job title is, because they just refer to me as professor, and I'm not like a full professor here, right? So I need to put it on my LinkedIn. Two parens. My typesetting will improve over time. If you happen to be going over these slides at home and you see something like, why are there two parentheses here, put it in Discord or send me an email or something and just provide the link. That's the easiest way for me to find what page it's on. I would love for these slides to be good because Professor Sipser's slides are in PowerPoint and I think they're going to be hard for people to use. Someone should have made these already and I couldn't find someone that made them. Okay. What's theorem 2? Well, we say every machine that's a non-deterministic finite automata can be modeled as a deterministic finite automata. And in fact, this is probably a lot easier than it sounds, right? All that's going on here is we only change one thing. We take all of the states in the NFA, and the same way we took pairs of states in the union, we're going to take sets of states, which means there could be 0 or more, right, up to n. Now, Q, this Q, the first Q, is some finite number, which means that we can call it, say, n, and we can say, there are n states in MNFA. And we can say, well, to track whether I'm in or out of n states, that's only 2 to the n possibilities. We can say if something is red or not, if it is green or not, and it is blue or not, and that is 8 possibilities, 2 to the third, right? So really what this is this is 2 to the power of the cardinality of Q states. Everything else is unaltered, but that's how we're going to refer to them. I think of these things as bit strings. They have a 0 or a 1 for whatever state is being currently tracked. If I were to write code that does this, I would write a Python list, and there would just be true and false all the way down the list, or 0 and 1. It makes no difference, and that would just determine whether I'm in state Q0 and Q1 and Q2, right? Delta, then, is unaltered. And why is delta unaltered? Well, this delta up here is a non-deterministic delta, which means it works over sets of states. This delta down here is a deterministic automata, which means it works over only states, but the states over which it works are themselves sets of states. So these two deltas have the same type. This one's deterministic over 2 to the n states, and this one is non-deterministic over n states. We slow down by an exponential factor when we are moving non-deterministically, okay? The only change we have to make is, since our states are sets of states, starting Q1 has to now be in a state. It's the state that contains only Q1, right? And then what do we do here? Well, we take every subset of the power set, so every possible combination of states. And if any one of those states is within the set of accept states, then we accept. Thinking about non-determinism is pretty useful for basically some cryptographic algorithms, which assume you can't proceed non-deterministically. And when is this useful, right? So if I can figure out a secret, or if I can encode a secret deterministically that can only be uncovered non-deterministically, then I gain 2 to the power n advantage over my opponent. I've been working on something called the RSA cryptographic algorithm. Have you heard of this one? It's public key encryption. You'll take a cybersecurity class if you haven't. And the way it works is it takes n time to make the secret and 2 to the n time to find the secret. So people simply say, my secret will have a length of 2,000 bits, and 2 to the 2,000 is a very, very large number, so it is very difficult to determine the secrets, right? And that's where this sort of non-determinism becomes useful, often in practice, if people are doing cryptography, and in other cases, of course, as well. Okay, theorem 3 is concatenation closure. I seem to remember you liking this one, and I think the manner in which you liked this one is you liked these particular lines here. We take our 2 finite automata. The first one has 1 or more accept states. We take arrows from all of those accept states to the start states of the second finite automata. That's it. We have to update the accept states to only be the accept states of the second automata, and we have to update the start states to only be the start state of the first automata, but we just go all the way through this one and then all the way through that one. We have to do this non-deterministically, and the example I gave is, it's a contrived example, it's not that exciting, right? But, well, we can even do the username password example here. So I type in my username, and then I type in my password, right? Perhaps we have different machines that check both of those things, right? And so if I'm just typing, you don't know when I stopped typing my username and started typing my password. In practice, we require humans to click on a second box, which is kind of a clunky way of doing things, right? But, you know, you don't have to do that. Perhaps you just type them in one line, and then these machines determine if they work. And so the way you do that is you start running the first machine over the whole system. And then at every point in time, if, for example, I think my username is 12 characters long because it's C Deutschbein, and my password's length is none of your business, but we'll say it's 27 characters, right? And so what you do is every single letter of the combined username and password, you start running M1 at the first point, and you stop running it at every point from 1 to 12 plus 27, which is 39, right? So you just stop running it at 39 different points, and you see if it accepts at any of those points. And at every point for which it does accept, you start running M2 at that point. And you're not running it more than 38 times, and it's a deterministic finite automata, so it runs very, very quickly. And then the non-deterministic one just begins at all points in time, and it doesn't care, right? So not the most painful thing in the world. The one thing I do want to point out, we have to make sure that we are not having states of the same name or the same whatever. Because these are abstract mathematical objects, it's never clear if they're the same thing as each other unless they're already in 2 separate sets. So we make a note here where we say, however you combine these, make sure you have as many states as you started with. We can't say, there is a Q1 in both of these. No, those are not the same Q1. M1 Q1 and M2 Q1 are different states. And so we will find some way to describe them differently, and we will probably call them Q1 sub M2, or Q1 to the power of M2, or something, right? So that's concatenation. Concatenation's not too bad. When does concatenation come into usefulness? Well, later on, we're going to prove that a generalized, non-deterministic finite automata, which is a finite automata with regular languages on its edges, is equivalent to all regular languages. And how are we going to do that? Well, we're going to have a finite automata of many nodes. We're going to take one node out, and then we're going to perform a bunch of concatenations, hooking up all of the paths that went through that node. So we care a lot about this concatenation closure because it's what allows us to show the equivalence between regular languages and generalized non-deterministic finite automata. And we care a lot about that because it lets us prove properties about both of them more easily. And we care a lot about that because it lets us set identity and access management on a cloud server, right? So all of these things are related and they're being used every day right now. Okay, star closure. Now, when we take out that one node and we start hooking things up with concatenations, that node can have an edge to itself. Anytime you have any loop, it can look like this, right? And so that node to its edge to itself, in theory, if you're going from node X to node Y, perhaps from node, you have the API key to use your OpenAI token, and then you check to see if you have enough cloud credits to run your OpenAI API server, and then the next state is you are getting the response back from OpenAI. Well, maybe you have to check many times if you have enough credits. Maybe it checks every 1 second if you've used up all of your cloud credits or something. So maybe you go through that self loop 1 billion times, right? And so if you're going to go through that self loop 1 billion times, you need to make sure you have star there, because that means there could be many, many states between do you have your OpenAI access token and here's the answer to your OpenAI query. So we include a star. And one of the things that can happen is maybe your query takes 0 time, so you never have to check to see if you use the token at all. What this means is that we must also accept the empty set, where just nothing happens on that self loop. No problem, we can do that quite easily. The only thing that's a little bit subtle is we have to add something in front of our automata to make sure it works. So the important things to keep track of are here. We have Q sub 1. Q sub 1 represents the initial state of the finite automata that I'm working with. And that is different from Q sub 0. I create a new Q sub 0, and there's going to be a lot of infrastructure around Q sub 0. Q sub 0 joins the set of states, which means it has to not be a name that's already used in the set of states. Q sub 0 is the new initial state. Q sub 0 joins the accepting states. And then Q1, let's see what is going on here. Right. We have an arrow from the final accepting state that doesn't require any input at all, that goes to every Q1 that is a member of the finished state or the initial state. It doesn't matter if you go there, right? So, what's going on here? Well, with the concatenation case, we took a bunch of nodes and we plugged them back into the starting state of a different automata. This is essentially concatenating automata to itself. So all of those extra nodes we add from the accepting states of our automata, they go back and they connect to the start state of the automata. Then the only consideration we have is we have a little thing before we get in the automata that checks to see if we have the empty string and accepts if we do. So essentially this is the concatenation of an automata to itself, and then the concatenation of that automata to an automata that accepts only the empty string. And the automata that accepts only the empty string is also going to come in use when we try to do our atomicity lemma. So there exist GNFAs. And we've already discussed these, but what is the difference? This delta right here, initially we allow deltas only to be some letter in sigma. Now we allow it to be any regular language over sigma. What are the regular languages? No problem. I will show you right here with the atomicity lemma. A regular language can be any letter that is an element of sigma. It can be the string of length 0, which we have also denoted as little epsilon, right? The nothing. And it can also be the empty set. So we have a string of length 1, a string of length 0, and a set of size 0, right? Because this is the set that contains the string of length 1, and this is the set that contains the string of length 0, because languages are sets of strings. So the null set is the set that contains no strings, but that is still of the type a set of strings. It is reasonable to say, we have some L, yeah, we have L of M1 which is equal to this, and it is of type set of str. Ooh, that's not a set because that's a dictionary in Python, so I have to say this. Okay. And that is completely allowed. It's well formed. We can even check the type of L of M1. Okay. We cannot check the type of the contents because there's no contents in there, but if we could check the type, it would contain strings. And we can demonstrate that we can add a string to it. And then we can check type of, we call this elements A, for A in L M1. And we can see that these are str. And really what we want to do is say that the type is equal to some string. We'll do a bit string 0, 1. And then to see that we pass the type check, we simply apply all to this. So, and I think we can probably do this for perhaps the null string as well. So, what does this mean? In Python, there's this intuitive notion. If you have nothing in your set, you can't say none of them are strings. Or you can't say they're not strings, right? So it makes sense to say the empty set is an empty set of strings. And it equivalently makes sense to say the empty set is a set of integers. It makes no difference, right? The important thing is once we start adding things to this, we always consider them strings. Here's the string of length 1. That's this thing. Here's the string of no length, right? That's the empty string. And we also denote that little epsilon. And then here's the empty language. That's how they differ. Those are the three things. Okay, so we have all of these. As what is hopefully a simple enough matter, we quickly construct machines that accept each of these. For the first one, we take A, we place A within our delta. From Q0, if we read A, we go to an accept state, and then that is our only accept state. Simple. For the next one, we want to accept only the empty string. Oh, and this is wrong. That should just say Q0. That's all. We accept immediately if we read nothing, and we reject otherwise. And then for the last one, here's the only thing that matters. No transitions or no finite. Somehow you can't accept any string. This thing is returned by, we'll call it empty lang equals lambda x false. And so if you check something is in the empty lang, so nothing is in the empty lang. And this is different from the empty string, which just checks that there's no other strings. Right. Okay. This is wrong, so I'm going to correct it.
This thing I think you actually added yesterday or something.
How you doing with this one? This one make sense to you? Oh, I was imagining it was still up there. Let me correct it in front of you so I can talk through my process. Oh, people are messaging me. I'm not going to open that then. Okay. So, you should know how things work. All of this is in a repository called Compute. The repository is public. These are the websites we're viewing, and I'm going to open one and show you so you can believe me. Here's Sunday. That's what we're in right now. This is the same thing, right? This one is on the internet. This one is on my local hard drive, or solid state drive. I'm so used to having hard drives because that's my first job. And it's hilarious. There was like 6 months of my life I thought about hard drives, and I've just never moved beyond it, right? It was in 2012, right? It was so many years ago. Okay, so let's look at Sunday. When I open this thing, and you can see all of these online as well, and let me show you where you can find them on the open internet. I didn't provide you with a direct link to this, but I also don't think it'll be difficult to find. Perhaps I'll provide you with a direct link. QMD stands for Quarto Markdown. That's the language I use to create the websites. All this stuff is for rendering online. It's not pretty, but all of the clean Quarto Markdowns in here are just these QMD documents. So if you ever want to see how I write something, and one thing you can do, for example, if you learn a little bit of Quarto, you can compile this all into a book yourself, right? And perhaps I will do that someday, I don't know. And we can see the atomicity lemma right here. So this is LaTeX, this is Markdown, this is Markdown, this is LaTeX, and you'll see there's also some Python in here. Well, maybe there is. There you go. That's what Python looks like. Not too difficult to work with, I hope. So let's go fix the atomicity lemma. Oh, what am I doing? Okay, there we go. One of the things I can do in VS Code, and I don't know if you use VS Code. Ooh, that is small. Okay, we're going to close this. You can see here I have the LaTeX that I'm generating from this code. And what's wrong with this code? Well, this is fine. The first one is fine. It has 2 states. The second one is not fine because it refers to a state as an accept state that is not an accept state. So I'm going to clean some of this up. I am actually going to make a change to M1. I'm going to turn this into a deterministic machine. And you see that the parens around the Q1 go away here, right? Live type setting. Okay. We see that our accept state is Q0. And then I claimed that the automata, which recognizes the empty language, should have no accepting states. And I have the strength of my conviction, so I'm going to update this. Now there is one subtlety here we have to do. This is the way I specify the empty set. I say var nothing, and it gives me that little thing, right? So I have no transitions, and I have no accept states, right? Now, when I'm done with this, I'm going to close this here. I have this button here, or I can say Control-Shift-K, and that will render the Quarto document. And it's slow. Because, well, the way I say it, because it was made by data scientists rather than software engineers. Which is maybe you don't say that around the data scientists. Maybe you're like, yeah, your websites are fast. So you got to be careful with that. Okay. And then when it's done loading, we see here are my well-formed atomicity lemmas. And, oh, that one didn't update yet. Okay. I thought I changed them. Did I not? I thought I just changed this, right? Atomicity. Okay. Yes, that appears to not have changed. So, well, maybe that's why the slides are wrong. Perhaps this tool just doesn't work. That seems unlikely, because this is correct. And that is not correct. So someone, I guess probably me, will have to deal with that someday. Oh no, it's correct. It's showing up now. Okay. Let's look. Oh. It was reading from cache. It had a cached copy of the web page locally on my page. Okay. So what's going on here? I needed to update this as well. There is no sigma here, so we're going to take var nothing. And this is how I do theoretical computer science, right? I think different people do it different ways. But I just write it down in a format that's like relatively accessible to me, and then I look at the results, and if it looks wrong or it doesn't make sense to me, I try and change it. And I check my work with Professor Sipser's, right? But he didn't write these down. I wrote the automata down myself because he just said, imagine it can do this. And I said, I don't know what delta is. I'm going to figure it out. And so I just figured my delta out, and that was that. This runs much faster when you have a fast computer. And you saw it reloaded, no deltas, okay? No deltas. Everything accepts. Everything accepts. Another way to stylize this, well, I don't know if you want to do this, right? You could put you could put big Q here and say, like, we don't care what the states are. Only specify the initial state here and then specify that all states are accepting. That would be another way to do this. It's logically equivalent, right? And that's just one of examples of like how you can fiddle around with these things, right? So versus Professor Sipser, right? Because like this isn't my only job, right? I needed to take some time to actually understand this stuff. But that means I see some of these subtleties like, oh, there are like different ways you can specify this. If either this is null or this is null, you only need one of them to be null. There's just no reason for the other one not to be null, because the only thing you have to do is make sure you never get to an accept state. And there's two ways to do that. You can have no accept states, and then you can have no arrows that go to the accept states, because it's a graph, right? So this is one such way. Let's see. Let's make one other change, because I'm in here, and I want to show you another way to think about this. Languages are sets of strings. How many times have we said that? A gazillion, but like not enough, right? Var nothing looks like this thing, the null set symbol, and that's pretty tiny. Let me pull it up over here. Looks like that. This refers to a set, and this refers to a string, so I should actually not say that a language is just one string. So I'm going to put these in sets. And the way I do that in LaTeX is this bracket character is a special character in LaSCEC, so we have to escape it, so I'm going to escape it. Oh, it's not in sigma. And let's preview this. Oh, I can just mouse over it and preview it. And that looks good to me. I'm going to recompile. I think it's slower with all the LaTeX on the proof slides. Though the ones that have like the images in them, it does take time to render those as well. The computer has to think. And we see these are now sets. All right. When I'm done with that, I just check these into GitHub. I've made changes to 2 documents. I've changed the Quarto Markdown document, and I've changed the HTML document that is generated from the Quarto Markdown document. No one cares about these. Those are made up files that don't matter, right? We never see them. Git commit. Fixing atomicity at atomicity lemma. I push it, and it's going to show up on your screen in a couple minutes. Right? It takes some time for the website to be built on GitHub's remote servers, which is really annoying to me, by the way, because I upload an HTML file to the internet, and the HTML file is there considerably before it shows up on the hosted web page, and I don't know what their internal process is, but to me, to do one other side anecdote. This is already updated, right? It says now. The website is building, But why is it taking so long? Because this HTML page right here is already live on the internet. I can download this thing right now, and I can open it immediately. So all of the bits I need are there. And so, yeah, this isn't rendering quite correctly, or in some sense of correct, right? Because of just, it doesn't have access to all of the CSS files and things like that, right? But I don't know what's taking so long. Also, separately, depending on what you're into, right? This is one way to view all of the work of this file. I would probably just change these proofs to have a different color scheme. But if this is more readable to you, right? The schematic view isn't great because that was an inverted color image. So that looks kind of goofy, right? But I don't know, right? Like maybe this is a really easy way for you to read things. It's up to you. Python doesn't look great, but that's also just comes down to the theme I used to render the Python, right? You can just change that theme. So
Yeah, this is fine.
yeah. So anyways, whatever works for you, just be aware all of this stuff is around, right? And at any given time, you can just download an HTML document and just look at it. Be like, ah, that looks kind of like a textbook. And I think it does, right? I think these things are a little bit annoying, but are they really that annoying? I don't know. It's kind of nice to know when you're looking at mathematical text, right? And in fact, in my mind, this is how I perceive sigma.
When it's theory over that, but when if you are proving a theorem or something,
Yeah.
one symbol is from here to another, you can probably.
It's really just whatever works for you, right? You see some goofy things like this is how I make power set. It's called MathCal. I don't know what MathCal stands for. I'm assuming it stands for Math Calvin, but I don't know if that's true, right? Oh, you might appreciate this. So you know, you probably know Linux terminal commands. And I think I can't do it on Windows. Can I? Oh, I can. Okay. So I can say like CD downloads. When I teach this, or one time this happened. This only happened to me one time. My name's Calvin Deutschbein. Students thought you use your initials to change which directory in. So they were writing their initials. So I had someone whose name, I don't remember what their name was, but their initials were KW. And so they were like, oh yeah, I'll do KW downloads. And you're like, no, it stands for change directory, not Calvin Deutschbein. So now I always joke with them. There's the old media format CDs. I tell them that stands for Calvin Deutschbeins, you know. We like to have a good time in computer science. Okay. This is updated on your screen now. You have to refresh it, but I've pushed an update. Okay. Let's look at Theorem 5. If you see something on my slides that really annoys you, fork the repository and update it yourself. I won't be offended, right? I think that's cool, right? I made this mostly for you, but I put it open source on the internet because I want people to have access to it if they find it, right? I'm probably never going to be as popular as Professor Sipser, but between you and me, I think Quarto Markdown's a better way to write this than PowerPoint. That's why I rewrote everything, right? It took 40 hours, but I did it. And it was good for me too. So essentially, I learned the material to teach it to you by making these course materials, right? I could have just taught off of Professor Sipser's slides, and then am I really going to have the 5-tuple memorized if I read this once? No, but you're getting it now right after 2 days, right? So I did that before I taught it to you. This thing's not too exciting, but we say for all regular languages there exists some M, such that the language of the regular language is equivalent to the language of M. And how do we do that? Well, we just put M together, building it block by block from the atomicity lemmas and from the closure properties. So we just build this thing up over time. And if I were you, I'd be pretty worried that I'm going to get a homework assignment that says, hey, I need you to build one of these things. So look out for that. It's probably coming your way soon. The real thing I have to do is figure out how I want to specify the regular language set union stuff, right? So there's a built-in union in Python, and so I can't call my union union, right? So you have to think about some way to do that. But in fact, I think You can put the union symbol in Python and say that equals to lambda of none, or whatever else. It's not allowed. I was hoping I could use it as a character. Because I was going to say, oh, you have to define a function with this name, the special union symbol. But we can't do that. It'd be fun if we could. Okay. So, GNFAs, atomicity lemma. We've proven that. Okay. We're now going to prove two lemmas, a base lemma and an inductive lemma, that are going to support Theorem 6. Theorem 5, for all R there exists in M, and Theorem 6, for all M there exists in R. This is the equivalence between any FA, but including a DFA, and any regular language, defined by a regular expression. So how does this work? Well, the first thing we have, do I know what time it is? That clock's wrong. Okay. What do we have going on here? Well, first of all, we have one of these nice little boxes at the end of our proof. And I love those, right? So that's really good for me. What do we say? Well, we say our initial state is, we have a GNFA of size 2. Why is it of size 2? Because it has a start state and an end state, and that's all, right? And so we say that. We say, hey, we have a start state, and we have an end state. And those are our only two states. And we're not going to say anything about sigma or delta until we get inside the proof, right? So we're just going to say, hey, I got a GNFA, it has two states. Don't worry about it, right? And I say, well, okay, now that I've tricked you into allowing me to use a generalized non-deterministic finite automata, I'm going to get up to something. And the thing I'm going to get up to is I'm going to assign delta very cleverly. And I'm going to assign it so cleverly, I'm going to say, I'm going to take the exact regular language which I am supposed to accept. And I am going to make that the edge label from the start state to the accept state. Which means the only way to get from the start state to the accept state is to exactly provide a string that is accepted by the regular language. So this is logically identical. It's the exact same thing. It's just formatted as a finite automata instead of a regular language. Easy. Then we're going to do the inductive lemma, and how's that going to work? This is the kind of annoying one, you remember, where we take out one state. Okay, so we assume I have at least 3 states, because otherwise we've already proven it. And if I have at least 3 states, that means one of them is not the start state or the accept state. So I pick one of the states that's not a start state or an accept state. And something's going on with that state, right? And what's going on with that state, it has incoming edges from every node, it has outgoing edges to every node, and it has an edge to itself. So what this means is that there's a path through that third node that is neither the start or accept node to every other node. And I just find those paths. So I say, if I have a node X and a node Y, there's already some regular language connecting them. But there's some other regular language which goes through the node I'm trying to remove, which we call node I. And that is the language that goes from X to I, the language that goes from I to I an arbitrary number of times, which is star, and then the language that goes from I to Y. X to Y via I. It's the same way as if when I'm flying home to Portland, I can fly straight to Portland, or I can connect through Albuquerque. Or I guess I'd probably connect through Chicago would be more likely than Albuquerque, but you know, it's the same thing. And so one of the other things I can do in Chicago is while I'm in Chicago, I can ride the tram around the airport an arbitrary number of times. That's allowed. And that's the star. So I can either do that 0 or 1 billion times. I can still get to Portland. Well, I can't do it 1 billion times because I'll die. But these things live forever, right? So any finite number of times I can take the tram around the airport. And I don't think there's a tram at the airport in Chicago. I connected it through Detroit recently. Detroit has a tram in the airport, right? So I can take the tram around the airport. That's a self-edge. And then I get on a flight and go to Portland. Okay, how's that work? Well, we have a generalized non-deterministic finite automata. The only thing we do is we pop qi out of it. We don't change q naught, which is the start state, and we don't change q to the n, which is the accept state. But we remove all edges incident on I from delta, and we expand all of the remaining edges at delta with the possible languages that go through I. Not too bad. Okay. And that's our proof. We have the base case and we have the inductive case. We remove states until we have 2 states, and then we say, ta-da, here's your regular language. Really, one way to think of this as a proof. The other way is this is an algorithm to construct a regular language from a finite automata. Because over time, we can start with a non-generalized, just a regular finite automata, right? And by taking states out of that, we can turn the edges into regular languages, right? So, and that would perhaps also be a good homework assignment. I'm thinking about the homework assignments. I'm worried about, so one of the problems with a class like this is I could very easily give you like 100,000 hours of homework assignments, right? Because you don't actually know how hard anything is, right? And you don't know how hard it is for you, and you also don't know how hard it is for the student. But I think like if someone gave me the homework assignment to prove the equivalence of an NFA and a DFA, and I didn't already know how to do it, I don't know that I'd ever be able to do it, right? But now that I know how to do it, I can simply write the Python script in a couple minutes, right? So what this means is we never have any idea how hard things are, because the hard thing is having the idea, and we don't know if you have the idea or not, right? And you can't get the idea by just staring at the problem and thinking about it. If you're stuck, really what you have to do is go do preliminary results and build up to it. So it is an interesting problem, and you'll have fun. Okay. We're at about an hour, so I'm going to take a bathroom break, and then we're going to come back and do the pumping lemma. And you can get some breakfast or something if you want. But let's return here in 5 minutes. Yeah. All right. Yeah, I don't need to set a 5-minute timer. Okay. Alright, what have we here? View 4, okay. Isn't there another error here? Let's see. Right. Yeah, we'll go to the first thing. That should have all of these. And that should have one of these. I thought I fixed that. Aren't these parens wrong? Right. A.
Always.
Yeah. Should be R. Epsilon. Right arrow. Yeah, no, that's fine. Okay. It's cooked. Yeah. That's all virtual. What I think. Not a problem at all. No problem. I turned off display capture just because we were on break, and my computer is noticeably cooler. Like, the only thing my computer is trying to do is trying to remember all of the pixels it has and, like, throw them out of a wire onto the internet, right? Or it's not even out of a wire, it's over Wi-Fi. I'm probably getting bathed in radiation right now. Okay. Cool.
I think we are outlier, that's why it's taking too much load.
Yeah, it's not good, that's for sure.
That's
But
why your computer is eating up.
yeah, but I mean, come on, it's like load a web page and then screen capture. I know how many pixels there are. It's a 1920 by 1080 monitor, right? That's 2 million pixels, and I'm asking it to stream in 10 FPS, right? That's 20 million calculations per second, and I have a gigahertz processor. Like, I should have a billion more compute power than I'm using, right? Is that true? No, 1,000 times more. Okay, maybe that's why it's a little tough. Maybe it needs 1,000 clock cycles per pixel. But some of this stuff, like, really, I'm asking you to render that epsilon, and that's going to take you a couple seconds. That's just way too long, right? That's not that many pixels, right? So, okay. Did I fill this with water? Yes, I did. Yes, I did. Okay. Here's the atomist dilemma. I cleaned all of this up. Inductive lemma. We're on to the pumping lemma. Okay. You know what's going on here, right? Nothing too exciting, but lots of inequalities that look quite confusing. And unfortunately, every time we use this to prove something, we have to check all the inequalities. My sense is kind of everyone hates working with the pumping lemma inequalities, but it's dramatically easier to prove things with the pumping lemma than it's with anything else. So we just make the inequalities work. So here it is. If I have some very long string and some finite number of states, every time I read a letter in the string, I'm going to go to a state. It doesn't have to be a new state, but I'm going to go to a state. So if I have more letters than states, eventually I'm going to repeat a state. Wherever I repeat that state, I can take the string from the first time I go to that state to the second time I go to that state. And when I do that, I'm going to get some string, and I'm going to call it y. So that's y. And I can repeat y an arbitrary number of times. So any language that I can't repeat some y in means it's not a regular language, because that means it can't be modeled by a finite automata, because either you need more states, or you need more power, or you need more something. It doesn't really matter what more you need. The only thing that matters is, if I can't find some string that I can include an arbitrary number of times, it's not a regular language. Yeah. CFGs were, we introduced these right at the tail end of Friday, and you see the rate at which we're progressing for the material. This is exactly halfway through the review slides. This is 16 is 31 divided by 2 plus 1, right? Or ceiling, right? And so exactly at the end of the first day, we were halfway through the material we've covered, right? Among other things, I think students benefit from being persuaded that the way they're being taught makes sense. I think the way this course is being taught makes sense, and yeah, I cheated a little bit by just looking at what MIT does, but when you see the cadence, you're like, oh no, that adds up, right? Okay, what are CFGs? Let's just look at one. There's a rule. This is a rule. A rule takes a variable and replaces it with a string that is variables and terminals. How do we tell if something's a variable? Well, if it's on the left side.
It's variable, and the right side it's terminal.
Yep, very easy. So you've got it. Let's get going. Cool. Well done. PDAs. Push down automata. I would probably call them stack automata. You know, I'm going to Google right now if people call them stack automata. Nope, if you type stack automata into Google, it says you mean push down automata. So I guess that's why we call them push down automata. But, you know, I mean, it says stack automata on this page, right? Does allow access to and operations in deeper. Huh. I would not have assumed that's what stack automata meant. Okay, so that means a stack automata is as powerful as a Turing machine, I think. Okay, so we have a push down automata. And this means that we can only read the first element of our list. This is pretty reasonable. Back in the olden days, many years ago, I gave out paper midterms. And at the end of the day, I would have a stack of paper midterms, and I could only read the first page on the stack. And I could take the first page off the stack and put it somewhere else, and then I could read exactly one page again, right? So this is something that actually exists in real life, right? A stack of papers is the data structure of a stack. There is no difference at all, right? The only thing we do is we put it in a computer instead of on a desk. What's the goofiness here? Okay. This is the same as a finite automata, except for the inclusion of that character, and that character is called gamma. Doesn't matter what it's called. It would probably be confusing to use a Latin character like G for it. It would probably be confusing to use a Greek character like gamma for it. We just have to call it something. One way to do it is to just always write what set it is, right? You could say, it's completely reasonable to specify this as gamma equals, you got an A, you got a B, you got some of these, and you can't really write that in a programming language either. Wait, you can write that in a programming language? I've never done that before. Oh my gosh, you can just put ellipsis in a set. Did you know this? I've never tried before. Wow, okay. I learned something about Python, and I'm not sure what I learned, because that was very strange. Okay. Sorry, we gotta check one thing. Oh, it's of type ellipsis. Okay, I was gonna say what type is this thing? It's its own type. Okay. I cannot think about that right now. That's too stressful. Okay, so what do we have here? Finite set of states, same as the finite automata. Finite set of string characters, same as a finite automata. Oh, what's this thing?
Nothing.
I am also allowed to read no character. Why is that? Because I can stay in one place on my input string and just do stack operations as long as I need to. And I can't do it literally forever, because eventually I'll run out of stack. But I don't know, maybe there's a loop in the stack or something like that, right? The stack alphabet. I can write the same or different characters to the stack, but I'm under no obligation to use the same characters for the stack as I do for anything else. The example of a time we had a special character for the stack, so we said, how do I see if the stack is empty? There's no way to do that in here in this transition function. There's no notion of is empty, right? In Python, we can say something like len of an empty list or something. We didn't write len, so we can't use it. So what we say instead is, I'm going to have a special stack empty character like Octothorpe, and it's the first thing I'm going to put on the stack when my machine turns on. And if I ever read that, I will pretend that's like the stack being empty, even though there could potentially be 1 billion characters after that. I just agree with myself that means the stack is empty. And in fact, that's what we do with Python lists as well. When they say they're empty, we just believe them, even though there's a lot of infrastructure in there, which we can demonstrate by storing things inside of them. Ooh, we can't do that. Let's see. Do I mean class? Sure I do. So there's still information in there. It's just not accessed the way we usually would, right? So even though the len of list is 0, there's stuff inside the list in some abstract sense, right? Ugh. My shoulders are tight. Okay, so what do? We've got some sigma, which we're reading. We've got some gamma, which we are also reading. I'm reading from the stack and reading from the tape. We will call it now at the same time. These things are non-deterministic, so I have a power set. We don't worry about that. We're just going to say we non-deterministically return a new state and a new stack symbol. And what's the new stack symbol? We can write something to the stack, but we don't have to. We can write nothing to the stack, and the same letter stays on top of the stack. Either one of those are fine. So we can either take something off the stack or not take something off of the stack. We can either put something on the stack or not put something on the stack. We can either read a letter from the tape or not read a letter from the tape, but we have to do one of those things, or we're not doing anything right. It would, of course, be a legal operation to say you go to the same state and you don't update anything. That is legal under this definition. It just isn't interesting. One of the ways to get around this when you're writing a proof is, we take the PDA that has the minimal number of delta operations. And you say, oh, okay, I'll just take the minimal one. Given a state, a letter, and a stack symbol, we get a set of states and stack symbols. That's all. An example of what this looks like is given state Q, any state Q, given some letter A, any letter A, given some stack character C, any stack character C. Perhaps I should put S there for symbol. Symbols, characters, digits, letters, I call them all the same thing, right? This is going to return a new state. But it's actually going to return 2 possible new states, or n possible new states, right? There's some set of new states. And they're going to have some new stack symbol. And perhaps this is a stack symbol, or perhaps it is not, right? Let's look at one way we could change this. R sub 1. So I previously didn't specify that this was inside a set. I don't really like specifying that in all of these cases we have to have a symbol. So I'm going to change this second symbol here to var epsilon, which denotes our empty set. Okay. I'm going to preview this, which I probably can. Actually, can I just preview this by mousing over it? See, that E changed to an epsilon, which to me denotes the difference between seeing some arbitrary character and the possibility of not seeing a single character at all, right? And it is also the case that this could still be R1. Perhaps I non-deterministically write a character to the stack. Doesn't matter. I'm going to save that, and I'm going to run this, and it's going to take forever to run, so I'm not going to come back to it. But that's one example of a way we can understand this. In state Q, reading A on the tape and C on the stack, either write D and go to state R1, or write nothing and go to state R2, I should say. Or write nothing, which is equivalent to var epsilon, which that stands for variable epsilon, because if you just put epsilon, it does set inclusion, like the other E. Okay. All right. This is the schematic view. I think you're pretty good with this. You've been good at remembering the stack. You've been good at remembering the tape, right? But this also, we recall, just so remember where we're at, we introduced the notion of no longer caring which state we're in. We no longer visualize that. We only visualize the stack and the tape. And this also introduced calling things the tape. Okay. Here's theorem 7. For all grammars that produce a CFL, so those are context-free grammars, there exists a pushdown automata, that is the 6th tuple, such that the language of the pushdown automata is equal to the grammars. Well, grammars are made out of terminals and variables, so we simply take sigma to be the sets of terminals, because that's what we're going to read on our tape. The language produced by the context-free grammar G is composed only of terminals, which means the input to our automata that is accepting those languages is only going to read those terminals. So sigma is equivalent to the terminals. We don't have to use the same characters as the CFG, but we're going to. We're going to say gamma includes the terminals, and it also includes whatever variables G had to use. In the case of our arithmetic example, where we derive A plus A times A, we used E as one of our variables, right? Delta is also going to be uncomplicated. Delta is just going to implement the context-free grammar, and it's going to implement it non-deterministically, so it doesn't matter which branch it picks. So the first thing we're going to do in our automata is from the initial state, we're going to go to state 1, the next state, I'm going to call it state 1. It doesn't have to be called state 1. And I'm going to write the starting symbol of the context-free grammar to the stack. And then I'm simply going to perform every substitution non-deterministically, which means that at some point non-deterministically I will perform the substitution that produces whatever string I need to have. So I create exactly the same acceptance condition as the generation condition of the CFL, because I only accept strings for which there is some derivation under the CFL. This one's a little bit interesting because it goes backwards and forwards, but it's not too bad. All right, here's the context-free pumping lemma. This one was kind of goofy, but in a way I feel like I understood this one perhaps better than the regular pumping lemma, right? And what's going on here? We take some long string. The long string is derived by a context-free grammar, which means somehow we have to add all those characters, letters, digits, symbols to the string. And the way we add all of those is by substitution rules in the grammar, which means we have a long chain of substitution rules. So I simply make my string long enough that my chain is tall enough that I have to use every terminal more than once, or I have to use any terminal more than once. I can also make it high enough that I use many terminals more than once, right? But like perhaps I only have 2 terminals in my language, right? So I'm going to run out of them pretty quickly. So I'm going to use the terminals more than once. Well, that means that there has to be some chain which I use the terminal twice in a row, because I can also make my tree tall enough to do that, so that every single derivation chain is longer than my number of terminals. So that means that sometime there's a terminal, variables. I should have said variables every time I said terminals. That I have enough variables that there has to be some variable that is present in the derivation of that variable. So I have an R on top of another R, or an S on top of another S, some variable on top of another variable. And so this means that a variable can produce 2 different possible outcomes, right? And you might think, what if all of my variables just turn into 0? That's fine, because then your language is under the pumping distance. So I don't care. I only care about things that are longer than the pumping distance, right? So what do I have going on? Well, at some point in time, my R can either return X or it can return VXY, because the internal R returns the X. What that means is every single time I see an R, I can either derive X or VXY, which means I can determine any arbitrary number of V's and Y's, which means this monstrosity, U, V to the I, X, Y to the I, Z, will always be present for all I. And it might be the case that Y, or V, is of length 0, but they're not both of length 0, so the concatenation of them is not of length 0, which I denote this way, right? And this means that I can pump context-free languages, and I can see if things are context-free languages or not. In the slides, I provided a few examples of context-free language proof, and I think for the context-free pumping lemma, I just literally showed only one thing. I was like, this is good enough. Get out there, have a good time. I'm not accustomed to using the context-free pumping lemma that much, so I think it suffices to know it exists. All right. We had much discussion yesterday, and we were trying to figure out how many elements were in the tuple that constitutes a Turing machine.
6.
That's what I was thinking too, but look, there's 7. Q, sigma, gamma, delta, Q naught, QAC, QReg.
Q naught and Q acceptance aren't the same?
Nope. We start in Q0 and we end in Q accept, right?
So that means the Q0 is the Q acceptance, right?
It could be, but they don't have to be.
No, acceptance. Okay, sorry.
Yeah.
I got it.
Yeah, so perhaps,
Initial state, okay, got it.
yeah, we could call it Q init, for example, right, instead of Q0. And actually, I kind of like that better, right? I could just say Q init here, right? Let's change it. Let's see, Turing machine. See, it's goofy, even just looking at this in the text, right? Why is this ACK reg? We might as well put init here, right? It is the initial state. Or we could put start, begin. You know, Q0 is perhaps clear enough, right? But it's odd because perhaps this should then be Q true and Q false or something like that, right? So I'm going to change the name to Q and N. And it doesn't really matter, but I'm going to do it. Okay. What's going on here? We have some input alphabet. This is a little bit novel, right? So the other Turing machine, or the automata, they read some input. And that input is written in sigma. Sigma is equivalent to, most importantly, the terminals of the context-free grammar, right? But it's also equivalent to the sigma of the regular language. Okay, so I have some sigma. The Turing machine is allowed to write to the tape. It doesn't just read the tape and say, yes or no. It writes to the tape. And so this means it can do other things, like it can write a book, you know. The Turing machine is writing to the tape, and it can write letters to the tape that are not present on the tape when it is provided as input. And the classic example we used is the tape break symbol. If it is pretending to have more than one tape, it can write an octothorpe, or it can write a note to itself, or it can write the name of one of its internal states, which is very odd, very spooky, right? It can write down its own representation as a string, right? And so the tape alphabet, which is gamma, is a non-strict superset of sigma. It can contain more letters, but it definitely contains all of the letters of sigma, because the Turing machine can definitely read and write every letter that's already on the tape, right? Its transition function is sort of unexpectedly non-goofy, we'll say. A Turing machine has some internal state, which we think of as program memory. It reads some letter off the tape, and it could be a letter it wrote, or it could be a letter that started there. So we just say it's one of gamma, right? And then from there, it is going to change its internal state. It is potentially going to change the letter on the machine tape. We don't have to say this is equivalent to potentially epsilon, because it can just read and write the same character. That it's logically equivalent to reading nothing, right? But we don't have to have the little subscript epsilons, which are actually much nicer. I think Turing machines are a lot more stable than push-down automata. And then it has, what is this? It either goes to the left or to the right, or to the up or to the down, or to the positive or to the negative, or to the east or to the west. And we just say, we just mean left and right. We're just moving back and forth on the tape. We don't care how we move back and forth on the tape, right? And so how do we express this? Given some state and some letter, we get a new state and we get a new letter and we go to the right. That's a Turing machine. Turing machines are markedly easy to work with, or markedly more easy to work with once we allow them to have multiple tapes. So how do we do that? Well, we double the size of our alphabet and then add one additional character. And what does the double mean? Oh, I should have just used capital letters for this. Oh, I remember, I didn't use capital letters because there's no such thing as capital 0. Because I was going to say capital B is the B where the head is, right?
Numerical value.
Yeah, but there's no capital 0. What I could have done, though, this would have been terrible. This could be positive 0. So 1 and positive 1 are different characters.
You could use O instead of 0.
Yeah. And then what do I do for 1? I don't know. Anyways, so basically, we can just think of doubling the characters as we can add a tick mark, you know,
Yeah,
and it doubles the size. And then we use the special tape break symbol, I call it, octothorpe, hashtag, £, end of file, whatever you want. Very easy to stylize it as an octothorpe, so I just made this selection visually. And then this example also includes something we papered over a little bit. The Turing machine tape is infinite in size. It just contains an infinite number of blanks. So there's always some blanks, which means no matter what computation we're doing, we always have space for it. Which means there's problems that Turing machines can solve that no actually existing computer can solve, right? Because they can use unbounded memory. We proved the same result for non-deterministic Turing machines. With the benefit of multiple tapes, this is easy. We simply write down the Turing machine on each one of the tapes, and then we simulate the Turing machine on that tape. And if we need a work tape, we can use that too, because we can have any finite number of tapes. And I gave the example of branching logic with exponentiation by squares, which which is something I wrote recently. So we check to see an if statement, and rather than evaluating the if statement, we simply execute both sides of the if statement on our non-deterministic Turing machine. And every time we execute something new, we instantiate a new tape. And it's very easy to instantiate new tapes. Here I'll show you an example. Here's a new tape. What's the letter after L, L, M? Here's a new tape. Here's a new tape. Here's a new tape. And I can do this very many times. No problem. I can have as many tapes as I want. Is that true? No, not as many as I want. But a Turing machine can have as many tapes as it wants. Because Turing machines are faster than Python, because they're imaginary. There you go. Oh, you can feel the lag a little bit. You see how it doesn't just instantly change the screen? There's a little bit of scrolling or something. Yeah. Let's stop overheating my computer. What is it? I saw a funny joke once about graphics, and it was imagining a conversation with the computer, and it said, computer, here's a triangle. Can you render this triangle? And it says, yes, of course. And it's like, computer, here's another triangle. Can you also render this triangle? And it's like, yes, of course. Here's a third triangle. Can you render this? Yes, of course. Then here's 1 trillion triangles. Can you render all of these? And they're like, no, absolutely not. Right? Like, why did you go from 3 to 1 trillion? But of course, that's just modern game design. They're like, I can probably render 1 trillion polygons. It's like, no, you can't. You can measure some like large number of thousands of polygons or something, right? The Church-Turing thesis, every effectively calculable function is a computable function. What does this mean? I spend a lot of time with statisticians, and they do this thing called a multiple regression, which is some relatively mathematically complicated operation where you're predicting some outcome from more than one input variables. And one of the examples they always use is, my partner does this in materials science. She makes their semiconductor quantum dots, and they degrade over time. And the rate at which they degrade is a function of the humidity in the room, the temperature in the room, and the wattage going through the bulb. And so how do you predict how long your quantum dot's going to last before it burns out, right? Well, it's some function of those 3 things. And so I guess in the early days of statistics, writing a function that takes 3 different variables and then predicts how long something's going to last, that was relatively difficult. That was called a multiple regression. The entire field of econometrics grew up around this, right? That's a calculable function. So my computer can take any number of multiple regressions. It might overheat at some point, right? But it is quite trivial to take a multiple regression now. And it was maybe very hard in the 30s when they could theoretically calculate multiple regressions, but no one had their hot new startup out of Silicon Valley that could do gradient descent and machine learning, right? So to me, this is interesting. An example of a calculable function is a multiple regression over, for example, 1 trillion data points, right? And a computable function is that same thing. If it is calculable, I can run it in a computer. Okay. We have just a few theorems now, and these are the acceptance theorems. One of them is the acceptance problem for deterministic finite automata. I want to motivate this a little bit because I think it might be non-obvious what we mean by acceptance. Okay, so what we mean by acceptance is, for any DFA, I can write down the string representation of that DFA. And we know we can write down the string representation of that DFA because we wrote it down in Python, and we proved that. But we also understand that theoretically, it is a calculable function and therefore a computable function, which means a Turing machine can compute it, right? Okay? So we write down the string representation of the DFA, and then separately we write down the word that we are asking it to accept. So this language is all possible DFAs and all possible words that those DFAs accept. So this is not a finite number of strings, but it is a countable number of strings, right? Nothing too exciting here. We just say, well, the Turing machine can pretend it is any deterministic finite automata. Why is that? Well, it can write down on one tape the name of its current state. It can write down on another tape the letter in the string it's currently reading. And then it can write down on a third tape every possible state. It can write down on a fourth tape what the accepting states are, and it can just look at all the tapes at the same time and make comparisons across them. And this might feel slow if we're thinking of it as a single tape Turing machine, and if we're thinking of it as a multiple tape Turing machine, you say, oh yeah, I look at these three things and make a decision. I look at these three things and make a decision. All the delta operation of a DFA is doing is it says, look at these two things and then tell me the new thing. And you just do that over and over again, right? So nothing too exciting here. And I simply say, we can emulate the deterministic finite automata on the Turing machine, like so. The decidability criteria for a non-deterministic finite automata is slightly more complicated because we have to make sure we don't go into an infinite loop. The decidable Turing machines are only those Turing machines that always halt, and a non-deterministic finite automata might have an infinite loop where there are empty strings connecting two nodes and there's some cycle. And this really would have bamboozled us if we didn't realize that we can turn every NFA into a DFA, and DFAs don't have those types of nodes. They don't have those types of edges between nodes, right? So to avoid having the problem where this just says recognizable and might never halt, what do? We create some B prime, and it is of type deterministic finite automata. What makes it deterministic? Its internal JSON notation has a single string that has a single state that corresponds to each pair of states and letters, versus the NFA, which might transition to multiple states. So we have B prime. We have theorem 2, which says we can convert every NFA to a DFA. So we convert B from an NFA to a DFA using the result of theorem 2. We have some acceptance condition, and that acceptance condition is equivalent to D of A of DFA of B prime. So we just use the acceptance Turing machine for deterministic finite automatas. We use the conversion machine from theorem 2, and then we just accept the results of that. And that is the same as theorem 10, right? This one's a little bit larger, but what's going on here? Well, we have the sort of emptiness E condition for DFAs, where we say, what is the set? This is a set, that's why it's in the curly brackets. What is the set of the strings, these brackets means it is string representation, of the DFAs? So our language is the language in which all of the strings are a representation of a DFA. But not every DFA, specifically the DFAs for which they accept only the empty language, not the empty string. So these are the empty DFAs. They accept nothing. And how do we deal with this? Well, we're not actually going to do anything with the strings. What we're going to do is we're going to look at the delta function. We're going to take a breadth first search over the delta function, or a depth first search, or a transitive closure. We're just going to examine delta, and we're going to see if any of the accepting states are reachable from the starting state. Here's a simple breadth first search. It's inspired by Dijkstra's shortest path algorithm. There's other ways to do this. Shortest path is very easy when all of your paths have the same distance. You just count the distances, right? And in fact, you don't even have to write them down in this case, because we don't care how far we've gone, right? So it's that simple. We just see if there is some path from the start state to any one of the accepting states, and if so, it's non-empty. And we don't care what it contains, right? We just care that it's not empty. And if there's no path, then that means it is empty, and that doesn't bother us either. The equality condition is a little bit goofier, right? And so how's this work? We have two deterministic finite automatas, or they can be non-deterministic, right? We've shown that because we can turn them into each other. They can even be generalized non-deterministic finite automata, then we just have to work harder. So we take these two DFAs, and we want to say, do these two DFAs accept the same language? Simple. We run one of the DFAs on one tape, one of the DFAs on the other tape, and we say those two DFAs together are pretending to be one DFA that we call C. We're going to call it C. Why are we calling it C? We have to call it something, right? So we're going to say, those tapes over there, they're pretending to be DFA C. And then I say, not to worry, I have yet another tape here. This is the emptiness criteria, which I helpfully just proved, right? I just proved I can see if things are empty. Well, I'm just going to see if the XOR, the exclusive OR, if the set of strings that is accepted by A and not B, and the union of that with B and not A, I'm just going to see if that thing's empty, right? And that's just some deterministic finite automata, right? And if the XOR is empty, then there's no string that is only accepted by one of them, which means they accept all the same strings. A little bit goofy. I think this proof would make more sense if we had shown this closure property previously. It's just not an interesting closure property to show, so we just assume it, right? And there we have our first stretch break. Let's do a time check. Right, I don't know what time zone I'm in. What time is it?
10:40.
10:40?
14.
14, okay, cool. We're going to do emptiness, then we're going to do diagonalization. I'm going to take another bathroom break first. I have to be well hydrated today because I'm on the plane for a while. How's your breakfast? Is that okay?
Yeah, it's good.
Okay, I think this is your last chance in person to ask me about any of those results we've gone through. Do you have any questions you want to ask, or are you just going to figure out anything you don't understand on your own?
I'll try to do my own.
Okay, cool. And of course you can ask, it's just, while I'm sitting here, maybe it's easier to ask. That's the only consideration. Okay. I thought it made more sense to take a little bit more time with the review to make sure you're in a good position before leaving. And in fact, reviewing 16 hours of lecture material in 90 minutes is still pretty fast, right? So what we're going to do is we're going to fly through emptiness and diagonalization. It's possible you've seen diagonalization before. It's taught in many math classes. And when I say diagonalization, do you know what that means? Okay. It's the proof that the real numbers are bigger than the rational numbers. So I'll show you that versus all this other stuff I've shown you. I think it's going to be very easy to find a YouTube video you like that explains diagonalization. So I'm spending less time on that as the decision I'm making, right? These emptiness conditions are a little bit novel and a little bit interesting. I've really only ever seen them explained by Professor Sipser and like my undergrad professor who I didn't understand, right? Who was lovely. I don't want to say anything negative about that person, but I didn't understand that class, right? Now I understand it. So let's do some emptiness. And what we're trying to do here before we leave for today, we've used essentially Turing machines to prove some properties about DFAs and CFGs. We haven't done CFGs yet, but we're going to do them now. We're also going to use Turing machines to prove properties about Turing machines. So right at the end of this block, we're going to prove the very first property about Turing machines. And then we're going to prove the hard property about Turing machines. And that will essentially finish the computability theory section of this class, right? I was hoping we could do it this weekend. I just don't see any way to go fast enough to do that. When I originally was looking at this weekend, I was imagining we would have all of today, which in fact you could have, right? But I didn't know that. So we'll have to finish that once we go home. But I'll at least show you one result about Turing machines. We will at least have covered computability theory. And that counts for something. Okay, let's do some acceptance. Okay, so we're going to do the acceptance criteria for CFGs. This is the same. I have some way of writing down a CFG as a string. I have some way of writing down a string as a string. That one's pretty easy. It's already a string. But I might want to do something like, say, this is a string, or include it in quotes or something like that. So maybe I have some special characters I use to denote it's a string. We skipped some slides yesterday on string encoding. You can go back and review them. You can decide if you think they're important or not. CFGs can have infinite loops. And why is that? Because we can substitute R for S and S for R and R for S. That's allowed. There's no law against me including that in my CFG. Well, what this means is we have to be slightly clever, right? And so how are we going to be slightly clever? Well, we have to make sure that we have forced our CFG to have some specific form. So what we're actually going to do is first we're going to generate an algorithm that's going to transform a CFG into a special form of CFG that can only perform a finite number of substitutions. And we're going to show that the two CFGs are equivalent. So then our Turing machine is going to wake up and it's going to look at a CFG. And it's going to say, I'm not going to try emulating that thing. I'm going to create another work tape over here. And I'm going to translate that first CFG into my special form of CFG that I know will finish someday. And that's called Chomsky normal form. And it's okay, this one's named after Chomsky because no one else came up with it, and I don't think anyone else uses it. This is Chomsky's normal form. Okay, Chomsky normal form, CNF. I want to reveal to you at this time that this was the step that I was sure a large language model could do. I said, this is so easy. I'm going to give you a grammar, and I'm going to ask you to write a Chomsky normal form of the grammar. As I was doing this, on my Lagrange email, actually, not my other university, I think like English professors and so on were talking about, they were sharing an article about how, the LLMs, they don't have great ideas, but their grammar is perfect. They understand grammar so well. And it's important to note that we don't, or to me, they do not understand grammar at all. What they do is they understand how to look like they understand grammar. But they only know how to look like they understand grammar that humans write. So there's nothing about a large language model that actually understands grammar. What they do is they're convincing liars, right? And the LLM tried to lie to me that something was in Chomsky normal form. And the problem with that is I can write a proof that something is in Chomsky normal form or not. And it's very difficult to write a proof that a sentence is grammatically correct. But it is very easy to see if something is Chomsky normal form. And what this revealed to me, unexpectedly, because I perceive Chomsky normal form as something actually very easy to do. It is a simple deterministic algorithm. It is only a couple steps. It is very easy to write in code. The only reason I didn't write it in code is I wanted it to be expressed in LaTeX, right? But I could have written this in Python in a few minutes. And the LLM could not do it. It could not do it when I said, is the answer you just gave me correct? And it said, no, it's wrong. And I said, can you fix it? And it said, yes, here it is. And it gave me the same wrong answer again. I mean, just hilariously inept, right? I don't know what the future of LLMs are, but if they can't do Chomsky normal form, it is very, very strange to claim they can do languages, because this is basically the best way in the world to do languages, right? And I think we know that. We know they're doing something other than languages internally, and I think what they're doing is being convincing liars, right? Chomsky normal form is a restriction on the types of rules we can have in a context-free grammar. And these are extremely restrictive, and you will see that they do not limit the expressive power of the context-free grammar at all. The first form is we take one variable and we translate it to two variables. That's all. By convention, they're different variables, but they don't have to be. And the other form is we take one variable and we translate it to one terminal. If you're looking at this and you've been thinking about the context-free pumping lemma, you'll notice immediately, this has a branching size of exactly 2. Every single substitution adds at most 1 character, which means that my pumping distance is always going to be 2 to the power of the number of variables. Very small, the smallest possible branching distance, right? Variable to terminal. Okay. The benefit of this is now we can very simply prove properties about every single substitution. And I gave the example of how much easier this makes the pumping lemma. Now instead of the pumping lemma being something to the some other power, right, it's 2 to the some other power. And we like it when things are 2 to a certain power. What is 2 to the 10th power? Do you know?
2 to the 10th power.
Yeah.
2 million?
Way too high. That's 2 to the 21st power. What's 2 to the 5th power? How about, can you do that one? That's a little more approachable.
10,000.
2 to the 5th power? 2 to the 5? Let me write it down. It's easier to visualize. Oh, it didn't recognize Python. Okay. 2 to the 5th power. Very good. What's this?
64.
So 2 to the 5th is 32. This is equivalent to, right? But 32 squared isn't that hard, and it shouldn't feel that hard for you. Because 32 is about 3 times 10. Which means you're going to get somewhere around 9 times 10 times 10. So 2 to the 10th is going to be 1024. When I said, you said, I think 2 million, and I said that was roughly 2 to the 21st. I think that's correct, and I'm going to try and prove it to you. That's 2 million, right? And why did I know that? Well, I know that 2 to the 10th is about 1,000, because it's 32 squared, it's 512 times 2. There's various ways to think of this, right? I know that 2 to the 8th is 256, because that's the number of, like, CSS colors, right? There's all these hex codes, like, oops, like that. Perhaps you've seen these, right? And 2 to the 56 times 4 is 1,000, and 4 is 2 squared, so that's 2 to the 8th times 2 squared, which equals 1,000, which means 2 to the 10th is 1,000. Oh, what did I do wrong? Oh, I used single equals. Yeah. If 2 to the 10th is 1,000, then 2 to the 10th times 2 to the 10th is 1,000 times 1,000, which is 1 million, which means 2 to the 20th is 1 million. Roughly. It's a little bit more. Yep. Which means that 2 million is 2 times that. Which means that if I want to know how much 4 billion is, it's 2 to the 32. 4 billion, almost exactly. A little bit more, right? This is very useful to us because that's the maximum size of a 32-bit integer. roughly 4 billion, right? And from here, we can also infer how big 2 to the 64 is, which it's 4 billion times 4 billion, right? Billion is 10 to the 9th, so we go to the 10 to the 18th. So we go from billion to trillion, quadrillion, quintillion. And then we also have 4 of those, so we're going to have 16 quintillion. Let's see if I'm right. A little bit more, it's 18 quintillion. I had a little bit of leftover numbers, right? And you see we're starting to get some spillover here. These are starting to get appreciably larger than 0. And I was modeling this as just 4. But if I say, for example, 4.3 squared, that is almost exactly this value. So you can just remember a few more digits if you're doing these approximations. Anyways, you never have to be able to do that, but I do powers of 2 in my head a lot. And one of the reasons I do them a lot is because I frequently am experiencing things that are useful to estimate with the powers of 2. The height of a derivation of a Chomsky normal form tree is a power of the string length, either forward or reverse, right? So a string of length 1024 has a tree of height 10 or 20, depending on how you count the substitutions, right? Okay, let's look at a grammar. And we're going to Chomsky normal formify it. So take this grammar over here. S can become AB or A. A can become epsilon or B, and that's lowercase b. And big B can become little c or big AB. We note that these things are not of Chomsky normal form, because not everything is of the form a variable becomes 2 variables, or a variable becomes a single terminal. So we're going to scramble this around. Let's put that on our left-hand side of the screen, and we're going to eliminate epsilon. How are we going to eliminate epsilon? Well, what this means is that everywhere there is currently an A, there can be instead a nothing. So how am I going to think of this? Well, that means S can become either big AB, little a, or just big B. And why can it be just big B? Because that big A can become nothing, which means S can become big AB or just big B, because we can have the little epsilon before the big B. So we can have, we just do one of the substitutions, little b, and then we also put the notion of epsilon there, right? We can do the same thing with A. The only thing A can become is B, which means there's no A left at all, right? We simply perform the same transformation with big B. We say it can be C. We say it can be little b before big B, right? This can become a little b, this A, or it can become just a B, right? Okay. That's wrong, actually. Do I have it open? I don't. Okay. I need to eliminate epsilon. Okay. All right. Now what we want to do is we want to eliminate substitutions where a variable is substituted for itself. So none of these are of legal Chomsky normal form, because they contain combinations of terminals and variables. And substituting S for B is not really great either. So how are we going to do this? Well, we're going to add additional variables as needed. We point out that this B here can be replaced by C, little b, big B, and little b. So we simply take where B is specified, and we substitute it in the rule, not in the string. So we take little b, big B, which, by the way, we already have in both of these, A, C, and B. And we do the same thing with big B. Big B becomes C, B and B, little b, big B, and little b. Okay? Now we're going to do something called eliminate long right-hand side. And what is a long right-hand side? That's when there's too much stuff on the right-hand side of a rule. We have two non-compliant long right-hand sides because we have a little b, which is a terminal, before a big B, which is a variable. I should have changed all of the lowercase characters to numbers, probably. Might have made this more clear. I wonder if that's true. I don't know. I'll think about it. Anyways, the LLMs couldn't do this, so I had to do this manually, which I shouldn't have to do this manually in 2025. Someone should have an AI that can write these slides for me. It's shocking that it didn't just fall out of it. I assumed this is what they'd be good at. But okay, so we need to deal with this problem, right? That's not allowed. The only thing we can have is a variable has to turn into two variables, or it has to turn into one terminal. So how are we going to do this? We're going to introduce a new variable. We're going to call it x. X wasn't used, and we can always have some new variable name. There's no limit on the number of variable names we can use. We can't use infinity of them, right? But we can use any finite number, and we're only ever going to need a finite number, right? Because we have a finite number of rules. So, no trouble. This is now two variables, or one terminal. This is Chomsky normal form. But this is just Chomsky normal form for one rule. We have to do Chomsky normal form for the entire grammar. So, we're going to do the same thing with b. We're going to use xb again. And then what can x become? Well, this thing is replacing a singleton little b. This thing is replacing a singleton little b. So x can only become singleton little b. We do have to add one rule, but we add one rule that brings us in alignment with Chomsky normal form. This doesn't look great to me, and I'm annoyed with it in the following ways. I would like all of my variable substitutions to be at the beginning of my list of possible substitutions, and I would like my terminal substitutions to be in some order. ACB is not well ordered, and CB is not well ordered, and we can tell that because even if we don't know the order of the alphabet, up here C comes before B, and down here C comes, okay, maybe that is in order. Maybe C just comes before B in this language. Never mind. I apologize. I was not familiar with CB's game. Okay. So I'm just going to reorder these, and I'm going to reorder them as so. S can become XB, A, B, or C. B can become XB, B, or C. And X can become little b. That's all. And so this is a Chomsky normal form grammar. Now, there was one error in this derivation that could have affected the entire thing, and I could not fix it in a short amount of time, so I'm not going to try to do so. Okay. Here's the lemma. Every word that is in a language of a grammar, we're using H for grammar. Why is that? H is alphabetically after G, and okay. And so we specified this is not a CFG, it is not a context-free grammar, it is a Chomsky normal form. Chomsky normal forms are a subset of the context-free grammars that are equivalently powerful. And we say each of these takes 2 times the length minus 1 steps. Why? Because to add 1 length to our string, we do a variable substitution, and then to resolve that variable substitution to a letter, we do a variable to terminal substitution. So that means every single character is produced by 2 substitutions, one which increases the length and one which turns it into a terminal. And then we get one back for free because we started with 1 variable. But we only get 1 back because we didn't start with a terminal, so we still have to do variable substitution on that terminal, or on that variable to turn it into a terminal. Okay, this is left as an exercise. This one's not too bad. This one's fun to write code for. Writing the code that turns one of these into another one of these is a good time. The thing about it that makes it unfun, and this is the persistent thing that's unfun about automata theory, there's not great ways to type these things into the computer. That's why I ended up using JSON, that's why I ended up using lists, that's why I ended up using lambdas, right? There's just no great way to type them in. But actually thinking over them is quite nice, and there are some languages that are better at this than others. I thought about teaching this term in a theorem-assisted proving language called ROCQ, R-O-C-Q. Prover. This thing, the ROCQ prover. I also thought about teaching it in Lean theorem prover. ROCQ is made by the French and Lean is made by Microsoft, and it's funny that the two different entities of the same type are the nation state of France and the trillion-dollar company of Microsoft, but in fact, those are the two people that make languages, right? And Lean is quite popular now. So maybe I will someday figure out a way to teach theory of computation in Lean. But not yet. So you can write this proof in Lean, for example. And it's a simple pattern matching thing. Theorem 14, decidable, ACFG. This is the thing we were trying to solve, and we didn't want to have infinite loops. I just took out my infinite loops by showing I can turn everything into Chomsky normal form. I convert the CFG to Chomsky normal form. I test every single string of that length. Not. I test every single derivation of that length. It's a finite number of derivations. This machine halts someday. And I'm allowed to use exhaustiveness checking here. No one cares how efficient my Turing machine is. And that's that. Corollary, what does that mean? We get all of the context-free languages. It's worth pointing out that we don't need to know what the Chomsky normal form is of a context-free language. We just know that there is one. And so we don't know the derivation of any given string. We just know that there is a derivation of any given string, right? This is a theoretical construct. And so one of the things to point out is that there could be some context-free language that perhaps we can prove it's context-free in some way other than by using a CFG. And so we don't know the context-free grammar that generates that language. We do not care. It suffices to know that there could be a context-free grammar. And if there could be a context-free grammar, there must be a Chomsky normal form. And if there must be a Chomsky normal form, there must exist some Turing machine that can process it. We don't have to know what any of those Turing machines or Chomsky normal forms or context-free grammars are. We just know that they exist. And that is sufficient for a proof, because we're just saying that something is true. We're not saying how it is true. Okay. We don't need to know how to do the thing. We just need to know that we can do the thing. Okay. Here's an understanding check. Is a PDA decidable? Yes. You simply convert the PDA into a CFG. Do we know how to do that? No, but it's in the book. We can figure it out. We can write the code if we have to, right? Let's do emptiness real quick. We're actually going to begin with equivalence. We have two CFGs. How are we going to deal with that? You can't really try every string because there's an infinite number of strings, and we have to finish in finite time if we're decidable. When we did equivalence for DFAs, this was the XOR, remember, where we had a machine named A and a machine named B, and we put them each on their own state. There's one problem with that. We never proved that CFGs are closed under anything. We didn't prove they're closed under union. We didn't prove they're closed under concatenation. We didn't prove they're closed under star. And in fact, we can't prove that. This is undecidable. There exists no Turing machine that can determine if two context-free grammars are equivalent. You can't figure it out. This is the first thing we've seen that no computer can calculate. This is not calculable. It is not computable. Given two context-free grammars, I cannot conclude if they're the same. This is devastating for software engineering and program correctness. Given two programs, I cannot tell if they're the same. There is no possible way to do that. Now, I could get lucky. They might happen to be extremely similar, right? But I can give one relatively simple example quite quickly. We'll open WSL. And so I'm going to use this example in the two programming languages I teach the most, which is Python and C. And I'm going to boot up WSL here quickly, or I'm not. Here we go. In Python, -1% 3 is 2. And why is that? Well, because if I add 2 to -1 and take that %3, oh, I do not like order of operations. Okay. It's equivalent. And so, what am I going to do here? I am sort of unaccustomed to this because I'm used to sort of modulos returning positive values in all cases. If I take the C programming language, have you seen C before?
Yes.
Okay. there's something ludicrously obnoxious about C. Wait, actually, I don't need this. I'm not going to print the value. I'm going to return it, and then I'm going to read it at the command line. There's also a modulo operator in C. This is pretty annoying. This returns 255. Well, I happen to know why that is because I know a lot about C and Python, right? But say you go to prove that some program written in Python is the same as some program is written in C. And you see that both of them have one of these things, and you see that both of them are used to calculate remainders of division. Good luck writing a proof that deals with this, right? That is a 2, and that is a 255, and those are very, very different numbers, right? Do you know why this is? This is the internal string representation of -1. It's not, it's a negative number, it's not equal to 2, it's not approximately 2, right? It's just the same as this number. It doesn't do anything at all. And that's because -1 is less than the absolute value of 3, right? It doesn't even perform any calculations. In order to perform, I think it's like Pythonic, where's my cursor? So I think to do this Pythonically, you have to like add the modulo back, and then you have to take that modulo again. And this is a way to force a modular value to be positive. And that's how we get 2, which is the same as this Pythonic mod. But I would not have concluded what was I doing? I have to see what was in the mod. And then Python C print -1%3, right? No! Okay. So I can get the same value, right? But for some reason, x%n plus n% in C is equivalent to % in Python. How do you deal with that in your grammar, right? Like, there's going to be stuff like this forever. And so just because of the level of complexity and how many strings can map to other strings, we get into real big trouble when we start to prove equivalence between programs and things of this nature, okay? We'll return to this with more robust proof techniques, but it suffices now to show that we have a problem, okay? The same thing is true for ambiguity. It is not possible to conclude whether a CFG is ambiguous or not. Why? Well, you kind of have to show that you have 2 different derivations for a string, and there's just a few too many of those things to think about. Why can we do the equivalency for DFAs and not CFGs? It's the closure properties. We don't have the closure properties over the CFGs. We haven't shown they're closed under union or star or anything else. Finally, we'll do something over Turing machines. Can we conclude that the string representation of a Turing machine and the string representation of a string, the set of languages that contain these string representations, so Turing machines with at least one string they accept, can we have a Turing machine that only accepts that language, which is decidable? We should get nervous about this pretty quickly, because I should be able to put a W here that this machine neither accepts or rejects, because Turing machines are allowed to not halt, right? Which means that if I can decide whether this thing is part of a language on a Turing machine, that means for all words, computation always halts. And how do I prove it always halts? Well, we haven't proven that yet. And we're going to prove that you can't prove it. But in order to do that, we're going to need diagonalization, which we haven't covered yet. So we're going to get an incrementally weaker result. And that result is that we can recognize. We can't halt, but we can return true if true, right? And this is simple enough. How are we going to do that? Well, easy. I'm going to create a Turing machine. I'm going to call this Turing machine U. Why is it called U? Turing called his first machine U. He did not necessarily initially propose Turing machines as having some arbitrary finite number of states. He actually tried to set the states that could compute anything, and I think he had like 7 states and 12 symbols or something. He was like, this can do anything, and I think that was later proven. So we're going to have some general purpose Turing machine, and we haven't really shown how to make these, and that's actually a big intellectual leap, but somehow we have some general purpose Turing machine. This general purpose Turing machine, what's it going to do? It's going to write down the machine M on one of its tapes. And on another tape, it's going to write down the current state of M. And on another tape, it's going to write the current head position of M. And on another tape, it's going to write the current W. And it's going to write all of these things down. And it's just going to emulate the Turing machine by moving around in its internal states, right? And U is going to accept as soon as M moves into an acceptance state. U is going to reject if M moves into a rejection state. But M is under no obligation to either accept or reject. It might loop. It might spin. It might hang out. It might deadlock. It might remember this one? It might do whatever that's doing, right? Is my computer getting hot? I can feel it. Using my computer as a space heater here. So what do we have to do here? Well, this isn't actually like a theoretical or logical problem. There's nothing we can do to make the Turing machine more powerful. There's nothing to do we can prove to make it halt. We can't add an execution monitor. We can't only accept the Turing machines that happen to halt in under 1,000 steps, right? That's pointless. So what do we do instead? We can't say if M doesn't halt, because we can't tell if it's going to halt or not. The only thing we have is a Turing machine, and Turing machines can't tell if they're going to halt. So how would we check that? We don't. We're writing a recognizer, not a decider, so our simulating machine doesn't have to halt. That's the weaker claim. The only thing we do is we accept from U if we accept from M, and then we make no claims otherwise. So it doesn't matter if U ever halts. We're just going to write it this way. We're not going to say U rejects if M rejects. We're going to say U accepts if M accepts, and then we're going to stop talking. We're not going to make any claims about whether U rejects or not. This will already recognize everything, and it will otherwise either reject or loop, but we don't care. That's already the notion of what it means to accept in a Turing machine. So one of the reasons that Turing machines can emulate themselves is they have the same halting properties as each other, which is very nice. So just to introduce this, U is the name Turing gave the machine. Who cares about this? Computer scientists who didn't exist yet, who came into existence because of U. Information scientists who cared a lot about bit encodings of things. So Claude Shannon is a famous one of these that did a bunch of early signal processing, and they got really into the theoretical work, right? The first people that showed binary strings could encode all information were having a good time. And then someone asked, can this binary string encode pi? And they said, uh-oh, we can't do that one. We need an infinite number of zeros and ones, and we don't have that many, right? It was relatively useful for the mathematicians, though for the most part they've passed that along to the computer scientists now. Very interesting to the philosophers, right? And very interesting to the linguistics, because what this means, the existence of U, means that all natural languages are also computable, because we can write them down as strings, right? Now, you might want to make some claims that a spoken language is different than a written language, and perhaps spoken languages do contain more information. That's a separate claim, but all written languages now can be processed by Turing machines. And again, if we think about all of the AI results, all of this was trivial in 1937. Of course a machine can write any sentence. We know that. That's not a hard thing to do. And it can write any sentence given any sentence. there is a 7-state 4-symbol universal Turing machine that was developed in 1962 using whatever a 2-tag system is. Do I know what a 2-tag system is? I think it's some way of making sure the tape goes both ways. The original Turing machine only had the tape go in one direction. So I think they use tags to see which way the tape is going, right? So someone named Marvin Minsky developed this in 1962. Worth noting that took 24 years. So it took a while to be sure these things worked, right? Turing, I think, thought he had one, and eventually it was found to be logically inconsistent under some cases, right? So people were making a lot of proof errors in these days, and I don't really begrudge them because no one really knew what a Turing machine was, so it's kind of hard to prove a property about them. Usefulness of U is just that we can say one of them exists. I want to point out that this is very similar to something Amber Huffman talked about, which was the RISC processor. RISC stands for Reduced Instruction Set Computer. RISC computers are open source computers that can perform all of the computations of the closed source Intel devices and the closed source AMD devices. They are equivalent in power, but they have many fewer instructions. And those many fewer instructions correspond to what? A smaller alphabet and a smaller number of states. Simple. So lastly, we have theorem 15. We take machine U simulates M on one of its tapes. It accepts if it accepts, and that's all. And here is our summary for today. We have 2 acceptance, 1 emptiness, 1 equivalence on DFAs and NFAs. And we have an acceptance and an emptiness on CFGs. We have some undecidable results, but we also show that one thing is recognizable, and that is the acceptance test for Turing machines. And with that, we're going to conclude for today. What this means is we are 1 lecture short, and it is the diagonalization lecture. I will probably just rearrange the website and then do diagonalization this week, undecidability next week, P equals NP the week after that, and then completeness. And I will see how many minutes it is taking to cover those things, and either cover Cook-Levin theorem or not. I would like you to see the Cook-Levin theorem, but I might just say, oh, your final for this class is to read the Cook-Levin theorem.
So how are we doing next week? You're going to live stream on YouTube or how?
So what I think I'm going to do is I'm probably going to add an additional column here, and it's going to say video. So there'll be the slides, and then there'll be me talking. Then I'm also going to provide the Quarto markdown, so you can just look at how's this work. So I think I should have showed you how to get to this more easily, right?
Yes, I use so.
Yeah. So I'll give you everything. I'll give you the slides rendered into HTML, the source code for the slides, the video of me talking about the slides, and then I will give you a problem set. And that will be what constitutes the week. And then on the 3rd of March, on Yinye gets you that week, and I get you part of that week or something, right? So your final will be due that day. We should note that we are essentially down a week because we were supposed to be out here on the 23rd, I think. So we're kind of a week behind. Separately, you can start looking at these whenever you want. My hope was that beginning the 13th, which is technically when this term starts, people would have access to their Lagrange emails, and I think you got access to yours like 2 days ago. Right, so you never got an email from me that says, hey, check out these talks. These talks are very brief, they're just an hour, and they're for people without your level of background. So you can just blast through these if you want to set up your Quarto books. Watch the website. I will send you emails to your Lagrange email, and maybe I'll update the Bright